Outliers. We all know them. We all hate them. How can these data points just be out of distribution, not in the training data, things that we haven't seen before, things that we don't even expect? Well, they suck. So today we're going to look at what you can do about it. Specifically, we're going to look at the paper Learning What You Don't Know by Virtual Outlier Synthesis. This paper presents a technique to generate what it calls virtual outliers, which are synthetic data points that are out of distribution. The core idea is that rather than trying to come up with data space out of distribution samples, this paper comes up with latent space out of distribution samples, which is much easier and much more useful. They're then designing a loss that pushes down the energy of the model wherever the outliers are and pushes up the energy wherever the data is. This paper is really interesting because it presented very successful results on a multitude of benchmarks, so definitely this technique looks like it works. However, when I read the paper, I was quite critical. I had a lot of criticisms, I had a lot of open questions, and that's why I've invited the authors for an interview to the channel. So this video right here is a comprehensive paper review. I'll explain in detail what is in the paper, what the method does, what its contributions are, what its experimental results look like, what is good about it, and what I think is bad about it. Then in the next video, released tomorrow, I'll interview the authors of the paper. The authors will have seen my review and therefore are able to respond to any criticism and any questions that I had. So be sure to check out the interview part as well, because it was really cool to get all my questions answered. As always, let me know how I can improve these videos by leaving a comment, leave a like if you do like, and I'll see you around. Bye-bye. Do you have audio of someone talking? Do you want that transcribed? Boy, do I have the product for you. Assembly AI builds accurate speech-to-text APIs, which means that developers can use these APIs to automatically transcribe and understand audio and video data in just a few lines of code. And this works in the traditional way where you upload audio and you get back the transcription, but they can also do this real time. So you get a WebSocket to their neural network powered backend, and in real time, it gives you back text for your speech. That's insane. But this is not all. They have a ton of features on top of that. For example, they can do summarization, they can do topic detection, they can do bad word detection, content moderation in your audio. And I have to say, this is really good. In fact, I have uploaded this video right here to their APIs, and the text you see on screen is the raw output of that model. So judge yourself how good it is. We'll actually try some Swiss German words on it. It is an English model, but we'll just give it a shot. Hochikastle, Gelleretle, Haferkaas. Oh well, isn't that great? So give them a try. They even have a basic free tier. Their documentation is super extensive. They give you walkthroughs and examples of all the parameters that you can send. They have a great blog where they describe different feature sets and different ways of applying their technology. And yeah, it's a really cool thing. Now, I've only scratched the surface right here. They do much more. They have features upon features on this, but it's best you check them out yourself. So thank you very much to Assembly AI for sponsoring this video. It's really great. Please check them out. A link is in the description, and I wish you a lot of fun. Hello there. Today we'll look at VOS, Learning What You Don't Know by Virtual Outlier Synthesis by Shifeng Du, Chaoning Wang, Mu Cai, and Yixuan Li. This paper presents a model that can do out-of-distribution detection in object detection networks, but not only in object detection. They show it on object detection, but it is a general framework for detecting out-of-distribution data at inference time. If this really works, this could mean a lot for, especially for safety-critical applications, networks that are deployed as a classifier or a detector somewhere, and they would be able to recognize accurately when they are presented with something they didn't learn at training time, like some out-of-distribution class. In this particular case on the left here, you see an image which is an object detection network at inference time. It has correctly recognized the car on the right-hand side. However, it thinks that the moose here is a pedestrian. It doesn't even classify all of the moose, but it recognizes there is an object and the class is pedestrian, probably because it hasn't seen mooses. What's the plural of moose? In any case, it hasn't seen a moose or multiple meese at training time. And therefore, it cannot classify it. And very often, these networks make very, very high confidence predictions for classes that they haven't seen. This paper tackles this and proposes this technique called Virtual Outlier Synthesis, to which we'll get to in a second. As I said, it's a general framework. They demonstrated on object detection, which is a particularly hard task, but this could also be applied to image classification. They do make the point that if you have an image like this and you haven't seen the moose class during training, most of the image will still be in distribution. Like this will not be a particularly out of distribution image, except for that small part with the moose. However, if you do object detection, then the object itself here is out of distribution. And maybe that makes actually their tasks as researchers a bit more easy, because they are less often in these ambiguous cases where like half the data point is out of distribution. In any case, they mention here that the networks that we currently have, they often struggle to handle the unknowns, and they assign high posterior probability for out-of-distribution test inputs. Now, why might that be? If you train a typical classifier, the classifier will just attempt to separate classes from each other. You see this here in the middle. This is a projection of the last layer of a neural network right before the classifier layer, so right before the softmax. So the classification layer, all it can do is it can lay linear decision boundaries essentially through the distribution of data points. So what the model does is it sees three classes right here. So this is class 1, this is class 2, this is class 3, and what it needs to do is linearly separate them. So it says, well, okay, this is not an ideal color for this. I'm going to just put my decision boundaries like this. And now I've essentially separated the classes, because all that is important to a classification loss is that, points in class 3 are away from points in class 1 and away from points in class 2. So that also means that the more away from classes 1 and 2 I go, the better. Like the more likely it is to be class 3, because all I've ever seen at training is samples from class 3, and my entire objective was just to make it, to push it away or distinguish it, discriminate it from class 1 and class 2. So obviously, if I go more into the direction of class 3, the network will output a more and more confident number about this being class 3, even though, as you can see, the data is all in this region right here, and out there is no data. Yet the network is still very, very confident. Red here means quite confident. An ideal situation would be if the network was very confident where the training data is, right here. However, again, we have the decision boundaries like this. However, if you go further out, it will say something like, wait a minute, even though this is not class 1 for sure, and not class 2 for sure, it's most likely class 3, but still, I haven't seen any training data around that area. So I'm also going to just output a low probability or a low confidence score. I'm going to say it's class 3, but I'm going to assign it a low confidence because I haven't seen actual training data in that vicinity. Now this all seems intuitive and makes sense and so on. Mostly that is because low dimensionality and high dimensionality data is very different and can deceive if you look at it in a kind of a very simple projection like this. You as a human, you see this data and you go like, of course, that makes total sense. However, it becomes very different if you look at high dimensional data. Note that there is a reason why our classifiers do the thing on the left, because the thing on the right essentially amounts to like a probabilistic model of the data distribution, right? The thing on the right
it has an idea where all the data is, right? The thing on the left, it just needs to separate data from each other. 3 lines are enough for that. The thing on the right actually needs to model the data in the latent space, which can become pretty complicated in high dimensions, and it needs some very, very distinct assumptions to make it tractable. So the right thing is essentially a generative model of the data, like a distributional model of the data, which needs a lot more resources and power, and could pull away resources from the classification task to be solved. So what does this model do? First of all, they have some notation right here, which I found to be, well, let's just first look at the diagram right here. So this is the whole model architecture. They have an input over here. So there's input X, right? I'm going to use the green highlighter, I guess, for this stuff. There's input X. You can see this is the input image. In general, first you have this proposal generator, and that proposal generator will generate bounding boxes. So some of these detection networks, they have 2 stages. First proposal generation, and then a sort of a post-processing stage where they assign labels to the proposals. So the proposal generator would simply ask, where are objects? Any sort of object. The objectness property, it sort of generalizes between objects. So it makes sense to train the object detector to just predict where are bounding boxes. In this case, it would predict, well, there's one here, there's an object, and there's an object here. And then it would pass on those two to the classifier to determine what's in the bounding boxes. And you can already see the object detector has done a good job. It detected that this thing right here is an object. However, the classifier, what can it do? It has to assign a label. There is no option for it to say, no, actually, this isn't an object. And previous methods have tried this. They've just added like an extra class for outlier. It usually doesn't work too well, because the reason is pretty simple. In order to do that, here on the left, you'd have to introduce like another line and say, okay, so I'm going to introduce another line. I'm running out of colors here. Introduce another line, like right here. So this would now be outlier space. Well, that doesn't cover this region or the region back here, right? So having a single class for outliers is sort of useless, because there are just so many places where outliers could be, and not just like a single slice of the space. So you'd have to have many. You'd actually have to have like a lot, and ultimately that amounts to exactly the situation on the right, where ultimately you're going to train a classifier that is a threshold between low and high density areas, and that's exactly a generative model of the data. All right, first stage is the bounding box proposal, this thing right here. Then you pass on the bounding box to multiple things. First of all, there is a loss that's simply concerned with, did you detect the objects correctly? So during training, the proposal generator would simply be trained with that loss right here. Now, everything here is backpropagated, obviously, but that would be the main loss to localize the bounding boxes. The second stage here would be the assignment of a label. This would be the so-called classification head. So that would take the latent representation that is generated, including the bounding box, right? So we're going to feed this through a neural network, and that will give us a latent representation. This H thing mean that they call that the latent representation right before the classification layer, and the classification layer would assign a label to it. And that would be the normal way of doing things, and now we augment that by a bit. Just to say, they formulate this here as saying we have a data set. The data set here contains X is data, B is bounding box, and Y is labels. So B and Y would be the labels, right? Those would be the things to predict. And then they say they split it up into two things. So first of all, the P of the bounding box, and then the one of the label. And I don't think that's correct. I think that's a typo right here. I think this should be the probability of the bounding box given X, not the label. And this should probably be the probability of the label given X as well as the predicted bounding box. Let's call this B hat right here. The predicted bounding box, so B hat would be sampled from this. But this is minor because the rest of the paper essentially treats it as I think I write it down. In any case, what they do in addition to that is they also have this classifier right here. The classifier that takes into a sample and the bounding box, and it tries to predict this number G. And G is 1 if the object is in distribution, and G should be 0 if it's out of distribution. So this is a binary classifier that classifies any sample into in or out of distribution, independent of what the classifier head says what class it is. So that would amount to the situation on the right, where if you're anywhere in this region right here, the classifier would still say, well, that's clearly class 3 because that's the region of class 3, but your other classifier would say yes, but the outlier probability is very high. The inlier probability is very low for that region. So you can do outlier detection at inference time. Now, how do we do this? We do this by generating these virtual outliers during training. Virtual outliers are essentially outlier data points that you synthesize. Now, what you could do, and they mentioned that, what you could do is you could train like a GAN. You can simply train a generative model of the data and then use that to sample out of distribution data. However, they mentioned that synthesizing images in the high dimensional pixel space can be difficult to optimize. Instead, our key idea is to synthesize virtual outliers in the feature space. So the feature space is if you have your image, right? And let's just talk about classifier. You feed it through a bunch of neural networks, and then here is the last layer. And all you do at the end is you have a classification head that classifies it into multiple classes. And this right here is just described by a matrix W. This is just a linear layer that goes from the amount of features, I guess D or something like this, to the amount of classes, C. That's the dimensionality. So in this space at the end, you would do, in this space right here, that's the space we've seen in these diagrams up there. Here is where we would sample the virtual outliers. So what we would do is we would look at our training data. Where does our training data fall? And we'd say, aha, okay, there is class 1s, 2, and 3 as we had it. Then we'd build a Gaussian mixture model of the training data. Essentially, we'd assume that each class is described well by a high-dimensional, by a multivariate Gaussian. They all share the covariance matrix, by the way. And then we would say, well, okay, given that that is the case, which ends up at the situation in the right, we'd sample data points from outside of those Gaussians, so that have a sufficiently low probability. So these would be these virtual outliers. We would just sample them anywhere where our Gaussian mixture model says that there is no data. But still, we sample according to the Gaussians. So we're not going to be like way out here in undefined space. Just because this is in our support set, we're still going to sample from these Gaussians, but we're going to sample until we get a sample that has a very low likelihood. So we're deliberately going to sample outliers from these Gaussians, and those are going to serve as samples for our outlier classifier. So then the outlier classifier, what it needs to do is it needs to find a decision boundary between these virtual outliers and the data. You can see I'm draw this right here. So there's going to be a decision boundary. Now, you can see this decision boundary gets quite a bit more complicated than the decision boundary of between the classes, especially, given that we do it in the last layer. So we'll go on in the paper a little bit. What we just said is going to come up in a second here. So they say, we assume the feature representation of object instances forms a class conditional multivariate Gaussian distribution. And they state this right here. So every class has a mean. All the classes share a covariance matrix, and they do calculate. They don't learn these things. They do just calculate them from the training data in an online fashion. So this is in the penultimate layer of the neural network, as I just said. They compute empirical class mean and covariance of training samples, and they do this in an online, in an online estimation fashion, which means that as they train the network, they collect the training data, and then in an online fashion, they compute these metrics to always be up to date. They do say here, we assume the feature representation is this Gaussian, they say see figure 3. And figure 3 is a UMAP projection of UMAP visualization of feature embeddings of the Pascal VOC dataset. And I'm not sure what they mean by look at figure 3. This is a UMAP. This is like a projection, a nonlinear projection into low dimensional space. If I'm not exactly remembering what UMAP does, but for sure this is a projection. Like, this doesn't convince me that the data is Gaussian. It convinces me that the data is kind of in one place-ish, right? It convinces me that all the blue points are closer, or most of the blue points are closer to each other than they are close to, for example, the green points here. Like that is what is convincing to me from this graphic. It is not at all convincing that in the original high dimensional space where they come from, they are somehow a cluster or a Gaussian even, or even that all of these classes would have the same covariance matrix, even if they were Gaussians. So it is a wild assumption, but it seems to work. So the result of the paper are that they are very, very good at this outlier detection. They reduce false positive rates by a lot. So it seems to work. I'm just saying this does not convince me. Or maybe I don't understand UMAP. Maybe there's something. So here is where they say they sample the virtual outliers from in this feature representation space using the multivariate distributions. So they would simply sample the virtual outliers from the Gaussians, but then evaluate them and only take them if their likelihood is smaller than some epsilon. They say it's sufficiently small so that the sample outliers are near the class boundary. These outliers would then be converted to the output. So this would be the output, the classifier head by the classifier matrix. Now, that is how they sample the outliers. And all good so far. I have a few concerns right here. For example, what you're going to teach the model is, successfully, if in the last layer before the classifier, there is a data point, and that data point is not where the training data is, then if this model works, it will recognize it as an outlier, right? What will not happen, and this seems, okay, what will not be the case if that moose right here, for some reason, right, an earlier layer already confuses it with something, right? An earlier layer thinks, oh, this, it's 4 legs, it's probably like, it looks like a dog, right? Then the moose will come to lie really inside of the dog class, because it would have the features of a dog, which the lower layers would have confused it. So you'd have to have done this technique in one of the lower layers, and there you could see that this is an outlier. But the lower the layers you go, the less your data, the even less your data looks like a Gaussian. I mean, ultimately you'd have to do it in the input layer, right? And there it becomes clear that this is just like a distribution of the data that you're trying to approximate. And in the input layer, certainly this is not Gaussian at all. So I think this only works for specific outliers. If there is an outlier that, as I say, has like the same features as some in distribution data, resulting that in the last layer they are inside of this cluster, then this method will not be able to detect it. Yeah, that is kind of my one concern. The other concern I've already said is that this separating these outliers is naturally a harder task, because as well, it essentially amounts to a generative or a distributional model of the data rather than just a discriminative classifier. So how are they incorporating this into training? Now, during training, we still don't know, right? We have, so up here, right, we have our loss right here for the localization. We have a classification loss, which is fine, is good. So our classification loss tells us if we have the class correctly, but we still need a third thing, which is this uncertainty loss. We are going to estimate the uncertainty, which is going to be our measure of how much how much the model thinks that this is an out of distribution data point or not. And how are they doing it? They are using the log partition function for that. So the log partition function is it's this thing right here. It's essentially what is at the bottom of the softmax if you use a softmax for classification. So if the f here is the logit of class k, so if this is the output of your classifier, and then you do a softmax in the last layer across your logits, the softmax would look like this, right? So you'd have the class y at the top, and then you'd have that log sum exp of the of all the classes at the bottom. So the bottom right here is kind of like a measure of how peaky your distribution is, right? If your logits are, one is just standing out heavily, then that is kind of a measure for low uncertainty, like you're quite sure about what you're doing. And if all the logits are kind of the same, then this they're all more even. So this measure is a little bit of an indicator of certainty, right? So this was already shown to be an effective uncertainty measurement for out of distribution detection. So what we're going to do is we're going to use this as a uncertainty loss right here. So what we're going to do is we're going to train, or not to train, we're going to have a logit based loss. So we're going to say we are going to use a sigmoid, and what we want is we want this measure right here. We want the we want this right here, which is one is the logit and one is 1 minus the logit. I can't remember which one is which. In any case, we want this measure to be high for in-distribution data and low for out-of-distribution data, or the other way around. We want the uncertainty to be high for out-of-distribution data and low for in-distribution data. So if we get a data point, we'll plug it in to this free energy. Well, the By the way, the negative of the log partition function is called the free energy. Sorry, I forgot to mention that. That would make some connections to even other fields of science. So we're going to take our data point and we're going to not plug it into the classifier, but just this bottom part of the classifier, right? To measure, is the distribution that we're getting very certain or very uncertain? And then what we want is that if we have a true data point, then we want the uncertainty to be very low. If we have a fake data point, we want the uncertainty to be very high. Okay? So by adding this loss right here, what this does is this trains our classifier to be more certain if the data point is real and less certain if the data point is fake, which ultimately, right, will result in decision boundaries like this, or certainty estimates like this on the right here. So the certainty estimate on the left would just be, if we just train the classifier objective, the thing will get more and more certain as we go away from the classification boundaries, if we look at this certainty measure. And now we explicitly train the model to only be certain around the data and to be, again, very uncertain around all the virtual outliers. So that's why you see blue anywhere away from the data. We explicitly train the model to do that. So our uncertainty classifier that we talked about, where was it? This thing right here. Our uncertainty classifier is not, in fact, an additionally trained model. It is simply us plugging a data point into this uncertainty measure, and during training we make sure that this measure is low for fake data and high for clean data. Now this loss, if I see this correctly, this uncertainty loss, initially it will directly affect this parameter set right here. Since we only generate the fake data in the last layer, the only parameters that are really affected by this loss in that case is the classification weights right here. However, implicitly, obviously, by saying that the true data here must have a high certainty or a low uncertainty, and by contrasting this with the fake data in the last layer, it may also be that through backpropagation, the entire network is shaped such that the latent space will be more optimal for doing this classification. However, I cannot conceive super well how this, how all the effects and counter effects and so on are gonna work out. But it would be interesting to think a bit more clearly through that. So what we're going to end up with is a probabilistic score for out-of-distribution detection. Our loss is going to be a mixture of these classification and localization losses and the uncertainty loss added with a given hyperparameter. So this is going to be our detector for in-distribution. We simply take we take an inference sample, we take the predicted bounding box, we'll plug it into this uncertainty estimate right here. So this here is this free energy. We plug it into the sigmoid formula here, and that will give us 1 if the classifier is very certain, and a 0 if it's very uncertain that this is in distribution data. We can define a threshold, and that's going to be our out-of-distribution classifier. So that's it for the method. They go through a bunch of results. Now I'll shorten the results by saying they're just very good at everything, like at the data sets they try against the baselines. They do ablations, and particularly noteworthy, for example, here is the false positive rate, where lower is better. And you can see if they would just to add an outlier class, this would hurt the performance quite a bit. like more than other modifications right here, which I found interesting to see. Yeah, they compare against other outlier detection methods, and they do have, I believe, some samples right here. Needless to say, yeah, I have my concerns, but it does work pretty well. So, and I'm just a person that looks at this paper for the first time and hasn't worked in this field at all and hasn't tried anything. So I'm going to give the right away to the authors right here. But let me know what you think, and I'll see you next time.